What if I told you that a mathematical concept originally designed to model a simple spring can change how we analyze seismic data? Today we're diving into the Teager Kaiser Energy, a powerful tool that helps geoscientists interpret subsurface structures. I'm Heather Beadle, the lead of the AASPI consortium at the University of Oklahoma. So from bright spots to subtle stratigraphic features, this TK approach is giving us new ways to see the patterns in the data, which will help us better visualize the geometry. So here's a preview of some of the improvement in the results using the TK workflow. This work was mostly done by my co-PI Marcilio Matos in Brazil. And you'll notice that there's some improvements in the imaging, kind of marked by those yellow arrows where we can see those bright spots. So we'll start with something surprisingly simple, a mass on a spring. In 1990, Kaiser noticed something fascinating about how energy moves in this spring system. So you'll notice that the energy in the mass spring system follows the equation, marked here by the red arrow, E equals 1/2 to the mass omega squared A squared. And then here's where it gets interesting. When we look at seismic wave energy density, we find an almost identical equation. The only difference is that the mass becomes density, and so this remarkably similarity is what makes TK energy so useful for seismic analysis. So the first thing we want to do is understand how we're going to calculate TK from the seismic data. So we all know that we start with the basic seismic trace. Okay. So what we're going to do is we're going to split it into two paths. So you can think about it as looking at the same thing with two different pairs of glasses. One path keeps it as is, and the other runs it through what we call a Hilbert transform, which basically gives us the imaginary component. So it's kind of like seeing the hidden side of our data. Now both parts go through the same two-step workout, if you will. First, we run them through these special bandpass filters that calculate the derivatives. The first one tells us how fast things are changing, like measuring the speed of our signal. The second one, it's measuring how that speed itself is changing, kind of like acceleration in physics class. So these aren't just any filters, they're specially designed to handle noise without messing up the timing of our seismic signal. All right, so now the magic happens when we combine these derivatives together in a way that's pretty elegant when you think about it. So if you remember potential and kinetic energy from physics, it's kind of similar. We're looking at both how much the energy is stored in the signal itself in the real and imaginary aspects. So we do this for both our original signal and its Hilbert transformed twin. And then comes the good part when we add these energies back together in what we call the complex TK energy. In this way, we're getting a 3D view instead of just the flat picture because we're capturing all the aspects of the signal's energy. And finally, when we run this complex energy through one more Hilbert transform to get our TKV, the Teager Kaiser variation, you can think about this as taking our always positive energy measurement and giving it some of the ups and downs that make it more useful for other seismic analysis tools. So each step builds on the last to give us a really robust way of looking at the seismic data. It's like upgrading from regular vision to having X-ray vision for seeing what's happening underground. Okay, so now on the left, we've got our original seismic data, our amplitude data, which you can think about as our raw footage. You can see those classic wiggle traces that tell us about the reflectivity of different rock layers. You'll notice particularly that there's a strong reflection package around 1100 milliseconds. That's marked by the green line. And so this is going to be what we're looking at when we look at the other panels. So now in the middle panel, we're looking at the complex TK energy version of the same data. So you can notice that it brought out that strong event around 1100 milliseconds in a slightly different way, so a different pattern that we're seeing. It's like turning up the contrast on a photo. The strong reflections really pop out now. And what's particularly great is how it smoothed out some of the high frequency noise while still preserving the important features. It's actually giving us a better picture of the energy distribution in our subsurface layers. All right, and then finally on the right, we've got our TKV, the Teager Kaiser variation display. And this is is really neat because it's taking that energy information and transforming it into something that oscillates kind of more around zero, like our original seismic data. But it's highlighting the energy variations instead of just the reflectivity. So you can see how it maintained the definition of the key horizon at 1100 milliseconds while giving us a slightly different perspective on the surrounding features. All right, so now let's see this in action and look at a real-world example from a data set in New Zealand's Great South Basin. We're going to start off, as always, with our input seismic amplitude data, just so you all can see what we're looking at. Now we've calculated the TK energy of the complex trace using the Hilbert transform, and we can notice that some of the bright spots that could indicate hydrocarbon accumulation stand out, as well as some subtle stratigraphic features like the prograding shelves. And then there's also some structural elements that were barely visible in the original data. Here we can co-render it with our seismic amplitude data. And so one thing to note here is that the co-render figures shows that the TKE and the TKV exhibit lower frequency than the original seismic amplitude volume. And so this is something that you're going to want to keep in mind because we're getting a little bit more increased vertical mixing, which can help you or hurt you depending on what you're trying to do. So now we're going to look at some time slices at around 1.44 seconds, kind of where I've put this red arrow. All right, when we look at the time slices, the advantages of using TK become even clearer. Here, the TK energy is revealing the channel systems on the right. We can see some synuresis in the center, and also the unconformities on the left-hand side of the time slice. And when we look at the TK variation, it does an even more spectacular job at revealing the unconformity, synuresis, and channel system. We can even use the TK variation to calculate additional seismic attributes on. In this case, I'm showing the energy ratio similarity broadband just from the amplitude on the left, and the same calculation but done on the TK variation on the right-hand side. And we'll notice that it brings out a lot more detail. And as before, we can co-render to reveal more details about the system in the time slice. And then we can also look at a vertical slice. So we're doing it here along CDP 4300, and it appears that there's new lineaments on the left-hand side of the time slice that we saw. They correspond to lateral changes in packages of reflectors on the prograding shelf, so it's helping us better understand those unconformities. We can also compare the vertical slices of the coherence attributes that we ran on the original data and the TK data. And so while coherence is computed on the original amplitude volume up top, it excels at crisply defining those fault planes and discontinuities. The coherence from the TKV reveals a slightly different story, kind of an enhanced story, where it highlights more subtle stratigraphic features and lateral changes in the reflection packages. So this is kind of a complementary behavior, which makes sense. The original amplitude coherence is more sensitive to sharp breaks in the data that characterize faults, while TKV coherence, with its energy-focused perspective, better illuminates more gradual changes in the rock properties. So this is a great example of how different attribute combinations can give us a more complete picture of subsurface structures. We can go a little bit further by breaking down the TK energy into different frequency bands using wavelet transforms. So this is kind of like putting on different pairs of glasses to see the same structure in new ways. Here I'm looking at the frequency range of 16 Hz on the left, 40 Hz on the right, and we can uncover some fascinating details. The bright spots you'll notice don't just appear static, but rather they show subtle variations kind of marked out by the yellow arrows. And these are exciting because they're telling us about thickness changes in our reservoir units. And even more interesting is the channel network, which is highlighted by the red arrow, which comes into a much sharper focus at that 40 Hertz frequency. So you can think about this as tuning a radio, where each frequency band reveals its own little piece of the geologic system. The lower frequencies might show us the broader structural framework, while the middle frequencies are perfect for seeing the reservoir scale features. And just like you might need a wide-angle lens and a zoom lens to fully capture a landscape video, we can combine these different frequency perspectives of the seismic to get a richer understanding of what's happening underground. So any of you that are interested in exploring this technique further or seeing more examples of across different frequency bands, we've got a lot more case studies and detailed analyses available on our website. So from a simple spring to sophisticated seismic analysis, the Teager Kaiser energy and variation is a great example of showing how fundamental physics can transform our ability to analyze and interpret seismic data. Thanks for watching.